Hey everyone, welcome back to Faraday Research. It is Sunday night, and yeah, we're doing some testing tonight. So I've got a lot of meters hooked up. I'm going to explain my setup. Everybody wants to see values and stuff like that. So tonight I'm going to show you values. I'm going to show you numbers, and then you can calculate all the stuff that you want and try to debunk whatever you want. That's fine. Alright, so basically got the pulse motor set up, Adams motor. I got my meter, my voltmeter set for 16 volts in this test. I will not be going any higher, any lower than 16 volts. Okay, to run the device, I got my watt-hour meter hooked up to this device. As you can see, it is pulling 1.5 watts just to start this up. So whatever figure I give you after this, minus 1.5 watts. Okay, so we're just going to simulate as if this were a battery. Okay, so whatever wattage that I present to you tonight, it's going to be based on what this is pulling, not what that's pulling. So later on, after we get everything running, I'm going to show you how many watts are being pulled from the wall. Okay, and you're going to minus 1.5 from that figure. Okay, that will give you the true wattage which I am actually using to run the device. Simple enough? Okay, so I got the device hooked up, power coming in. Now, I got two leads coming off here. That's my power out. That is going to this capacitor. This capacitor is 4,000 UF. It can handle 80 volts. From there, it goes to my inverter, which is 300 watts. And then from there, it goes to my lights. All right. I'll also have the voltmeter on here to show you how many volts I'm sustaining in the capacitor to keep the inverter running. Okay, as well as we're going to get the figures off here of how many watts is taken the Adams motor to run to sustain the voltage for the capacitor, which ultimately activates and starts up the inverter. Okay, now before we go any further, if you haven't become a member, bottom right hand corner, you can subscribe. Also, I have all the links below for my Patreon, my PayPal donate. If you become a Patreon, you get all the perks. You get to see all my schematics, all my ideas. Everything is there. Helps me support the channel so I can buy hardware to do my experiments. So, we're going to get it started. I'm going to hook up the electronics. So, this won't be part of the equation. I'm not too worried about running the reed switch and running the switching device to actually run it. So that's on a separate power supply. It's totally segregated away from the rest of the circuit. It's isolated. So we're going to leave this at 16 volts. We're going to get the motor running. And as you can see, I got full power at my lights. Now the lights are 40 watts. Okay? So right now, if you do the math, 16.1 volts times that by 0.64, say 0.65. It's about 10.5 watts just from the box. All right. Now, let's go here. It's pulling from the wall 13.6 watts. All right. So minus 1.5. And that'll give you how many watts I'm pulling from the wall to run this. You get it? 13.6 watts minus 1.5 watts will give you how many watts I'm actually pulling out of this to actually use to run this. So I know this will take 40 watts to run, so we'll base it on that for now. Take 40 watts and you minus, say 11, or 10.5 or 11 watts, whatever you want. It's showing me I'm getting more power out than I'm actually using to run the device. And you can see the lights are fully lit. That's 60 hertz. Alright. Now let's turn my power meter on. So right now, as it looks, I'm sustaining 11.3 volts in this capacitor. This capacitor is feeding my inverter. Without this capacitor, I can't run the device. So what this is showing me is if I had about 2 or 3 more of these, the system would work even better. So I gotta get another, maybe 1 or 2 of these capacitors. They're 4,000 UF, 80 volts. I'm only sustaining 11 in there, and I'm running these lights, and they're all lit. Alright, so let's look at the figures again. 13.7 watts I'm consuming from the wall to run the device, everything. But minus 1.5, so let's say 12.5 watts, okay? 40 watts minus 12.5 is basically I'm getting like double the power out than I'm actually putting in to run it. At just this box alone, it's showing me about 11 watts, give or take. So 11 watts, and I'm sustaining 40 watts. It's pretty impressive. So there are the numbers for you. So if you want to figure how many watts this is, 16.1 times that by 0.66 or 65, and that'll give you how many watts this box is producing to make this run. Alright? The number at the wall is higher. It's about 13.9 watts. But just to get the box started, it takes 1.5 watts. So take 13.7 minus 1.5. So we're pretty close to what is matching here. Within about a volt. Or within 1 watt. We're very close. Within 1 watt. So say it's 12 watts going in. And I'm running 40 watts. And sustaining it. So it shows I'm putting out more power than what I'm consuming to actually make that power. If you look at this, I'm only putting in 11.3 volts. So the capacitor is creating that buffer for the reactive power that this thing is generating. Now, if I were to disconnect, this is my new piezoelectric transducer. It's 60 watts. If I disconnect this right now, this whole thing would die. You cannot do it. This thing is creating the reactive power. And that's why reactive power can actually work for you in an electrical circuit. But they don't consider reactive power to be real power. So that reactive power that I'm generating here, I'm taking it and putting it, or sorry, before that, I put it into a full weight bridge rectifier, right there. It comes out here, goes to the capacitor, and now the capacitor is condensing it. Now it's making it into real power. It's like the beer bottle. You take a beer bottle and you pour it into a glass. At the bottom you got the beer, and at the top you got the foam. The top foam part is the reactive power. It's got the power, but not the energy density as the real power at the bottom of the bottle of beer. That's where the real power is. So we have to make this reactive power into real power. So we rectify it in the bridge rectifier, dump it into the proper capacitor, and now it's becoming real power. There's no more fluff anymore. There's no more foam. It's real power. It's sustaining at 11.4 volts that it gives me enough power and current to run the inverter, to run the lights. So, yeah, definitely it's a big win as far as I'm concerned, any way you look at it. So it's showing me that this system here is creating a huge amount of efficiency. It might not be still over Unity yet. I'm getting there. From what I could see, the numbers kind of speak for themselves. So yeah, any questions, comments, leave it below. Also too, we're dealing with high power now. All right, we're dealing with high voltage. So if you don't know electrical engineering, you're not electrical savvy, don't touch this stuff. All right, because I'm working at a power level now that it can kill you. So you gotta be very, very careful. When you're finished with your experiments, always discharge your capacitor, because that can give you the lifter of your life and actually can kill you if you're not careful. So always make sure, check it with a voltmeter, discharge it safely, and then, yeah, you're good. But if you're not electrical savvy, stay away from this stuff. It's high voltage now. This is not a toy anymore. So, yeah, the numbers speak for themselves. You know, I'm consistently holding 11 to 12 volts, 11.3, 11.5 volts, and I got enough current going into it. So this is showing me two things. One, I'm sustaining the right amount of power. Number two, it's also showing me I'm sustaining the amount of current needed to run the inverter. Because if I wasn't producing current, irregardless if I had 12 volts or not, this thing would not work. So this is demonstrating to me that I'm creating voltage as well as current. All right? That's very important. You know, that's where it all boils down to. So I'm powering 40 watts of light bulbs, and I'm doing it on 12 watts of power. So to me, that looks like it's over unity in my book. So, you know, because when I run under very small load conditions, like the inverter itself is not, the way they've designed it, it's not very what do you say, energy efficient. Not really by a long shot. I could actually run these lights without the inverter and just go straight from here to the lights, and I can light these up with less than a watt of power. So the question is why? Well, number one, the frequency is a lot higher. That's where you get your energy savings right there. And the amount of current in order to run those lights without an inverter is way, way less. I'm running it using devices that I can show you numbers, figures. You know, I got a consistent 11.4 volts going in that inverter. I know all these lights combined together are 40 watts and they're fully lit. All right. If they're flickering, it's usually because of the camera, but to me, they're completely solid. This number is not lying to me, because when I subtract 13.9 minus 1.5, what it takes just to run this on its own with no load, it's about 12 watts, give or take. Very close to the number that I'm getting here. So it's a very, very close, within one watt. So even if you were to say 12 watts this takes to run this, I'm okay with that, because I know I'm putting over 40 watts here. So I personally think I'm on the right track. I think, you know, there's obviously still work to do on this, make it better. Eventually I want to loop it. I did loop it last night with a 16 volt capacitor bank, and the thing would run for over 4.5 hours. So it's demonstrating the high efficiency of the system. So what this system really does is convert DC electric power into a high voltage reactive power. Then from there, I put it through a full wave bridge to make it AC and DC. Now it's under control now. Now I got a positive, negative. Then I take that, put it into the capacitor, which I have to get more of these. These things seem to be helping me out a lot. This one here is 80 volts at 4,000 UF. So I'm going to get more of these. And it's sustaining my 11.5 volts to power this inverter. So yeah, I think we did good here. If you liked the video, give me a thumbs up. Also too, don't forget to subscribe on my Patreon, and PayPal. All the links are in the description. That helps keep me going, get supplies I need for the experiments. This motor is performing amazing. And the other thing too, what I really like It's running consistent. Like, my numbers are staying relatively the same. So, yeah, it's working out good. The coil, I'm touching the coil now. It's cold. There is no heat whatsoever on this coil. And I'm putting in just over a half an amp. It's because of the spark gap switch. I'm telling you, start using the auto relay 12 volt relay switch. I'm putting in half an amp. My coil's cold. It's not warm at all. It's not heating up. Excuse me. So yeah, take it for what you want. If you think we got a winner here, give me a thumbs up, and all your questions, comments below, and we'll see everybody soon.